Welcome. So this is our second lecture of ELE 475, Computer Architecture. And in today's lecture, we are going to be learning about microcoded microprocessors. So these are microprocessors which allow you to reuse components and reuse data path components in order to make a smaller processor. And we're going to start our review, our first review of 3 reviews. And like I said before in the previous lecture, if you are watching this lecture and think, well, I've seen this all before, stick through the first 3 or 3.5 lectures. That's designed to be reviewed to get everyone on the same page for this class. So I'm David Wensloff. I'm a professor here at Princeton University in the Electrical Engineering Department. And let's get started talking about our second lecture on computer architecture. So a little bit about an agenda for what today is going to be about. We're going to start off by talking about microcoded microarchitectures. And then we're going to transition to talk about pipelines, basic pipelines, and review of basic pipelines. And we're going to talk about the basics of pipelining. Then we're going to talk about and talk about the frameworks which we're going to need to analyze other pipelines, or analyze pipelines. Then we're going to talk about structural hazards in pipelines. So these are problems where you might need to use a resource in 2 different locations in a pipeline at the same time. Then we're going to talk about data hazards. Data hazards are where you have one instruction or one operation or transaction which is dependent on another operation or instruction in your pipeline, but they're in different stages. So you might need to somehow interlock or control or stall between the different stages. And then we're going to talk about control hazards. We'll probably hold off on the control hazards depending on how far we get in today's lecture, and it might end up a little bit in another little snippet on the end. But in control hazard, we're going to talk about when you have an instruction which has to redirect the pipeline or change what the pipeline is doing, or the instructions flowing down the pipeline are doing. That is another form of hazard. OK, so let's start off by talking about microcoded microarchitectures. One of the big problems is you're going along. This is a problem that happened back when processors were first being designed, and you couldn't fit a lot of the processor in either a room, let alone, or nowadays on a chip. But one of the questions that comes up is, what happens when the processor is just too large to fit in a room or fit in a chip? How do you go about solving this? And this is not a question of how do you solve putting multiple processors on a chip or a room, but rather if you really can't fit a whole processor in a room. So this would be if you're building your chips out of, or you're building your, processors out of something like vacuum tubes or switches or electromechanical relays. You have to think pretty hard about what happens if your processor is too large. How do you cut down the size? Well, you can time multiplex the resources. So that's right. You can use a resource, and instead of physically building a bunch of resources and then connecting them together, instead you can build one resource which is in some way general purpose, and then you can use that resource and then use it again and use it again multiple times for one instruction. And this is called a microcoded processor. So let's look at a microcontrol unit and how one of these things works. So in this design, you'll actually have, here's the control lines which run to your processor. So these are a bunch of wires that are going to come out of your processor and are going to assert different things on ALUs, multiplexers, registers. And then you're going to have some way you need to drive this. So in a microcoded control unit, you're going to actually have a microcode address that gets decoded and lights up in a ROM fashion a bunch of wires. And some of those are going to turn on these control lines. And they're also going to be used in this calculation of the next state. Now, if you look at this, you can see that this actually implements something like a small finite state machine. But the one interesting thing here is that you actually have the opcode from the program coming in here. And effectively, what you can do is for each instruction you're trying to execute in a program, you can cycle through a little state machine for it. And you can have different state machines depending on the opcode that comes in here. So the opcode comes in here. You might have, for instance, condition flags or something like that coming out of your processor. So whether the instruction is a branch and whether the instruction is taking that branch or not. And what you can do then is take that along with a little flip-flop here, which will keep it in some piece of state or an address. You can actually step through a little state machine, which will do multiple things. And we'll look at this in a little more example of how one of these microcontrol units will hook up to a microcoded microprocessor or microcoded processor. Last thing I wanted to get across here is this is typically a ROM. And you can actually cycle through it multiple times. And the ROM is going to tell you where the next microcoded instruction is. So you'll be basically cycling around this loop multiple times, or maybe only one time, depending on the actual instruction you're trying to execute. Here is the microcoded control unit, or the microcontrol unit hooked up to a microcoded processor. So we have the data path sitting in the middle here. And we have a bunch of wires coming out of our control unit here, which assert different things on the data path. For instance, are you doing a subtract? Are you doing an add? And it's going to swing different multiplexers inside of this data path to select what operation is actually occurring. And I wanted to contrast the microcontroller, or the microcontrol unit, with the memory where you're actually going to store your user programs. So your user program is going to be stored in a RAM structure, or a randomly accessible memory structure, versus a read-only memory structure. So a good example of this is you'd have your actual ISA instructions here, like x86 or MIPS, sitting in your RAM. And up here, you're going to have microcode instructions. So if you go back to this diagram, typically the ROM entries are called microcode instructions. And sometimes people write little programs that say, how do you sort of control the different lines that come out of here? OK, so let's put this all together and look at how we would build a bus-based RISC processor. So we're going to build something like a MIPS processor, which you may recall from your computer organization class. And we're going to use a data path where we reuse data path elements over time. So we're going to time multiplex the resources. So this is not a pipeline design. And it's not even a single cycle RISC design. But instead, it is a microcoded RISC design. And we're talking about this because we are going to contrast this with pipelining in today's lecture. So let's look at this diagram. We're going to see that we have a register file here, which has 32 general purpose registers, because we're trying to implement MIPS, which has 32 general purpose registers. And we also store the program counter, or the instruction pointer, in this register file. So this register file actually has 33 elements. Or maybe you can store it in where the zero register is, or the zero register is in MIPS if you try really hard, because that's typically hard-coded to 0. So let's walk through how an instruction is going to be executed on such an architecture. And a couple of things to note here. This is main memory, so we're going to have to fetch our instructions from over here. Our ALU's here. And this is our instruction register. And everything is connected together on a bus, where only one value can be driven at a time. And that value can be broadcast to multiple locations. So let's start off by thinking about what do we need to do to execute an instruction. Well, to execute an instruction, we're going to start off by fetching the program counter for the instruction. So the microcoded control unit is going to assert the wires to basically say, do a read out of the register file here for the program counter. And we know that the program counter is going to be selected because the microcontroller control unit is going to set on the register select lines here, assert the entry which will choose 32, we'll say, which will select the program counter. So the program counter will be, this is all in one cycle right now. The program counter is going to be asserted onto this bus. And now we need to latch it somewhere in a register. So it's going to be broadcast all the way on this bus, but we actually want to take it and load it into this memory address register here. And that'll finish our first cycle of our microcoded control unit processor, or microcoded control unit processor. The next cycle, this is all within one instruction. we're going to fetch the instruction we need from the data memory and the instruction memory. So that is going to get forced onto this bus, and we're going to take it and latch it here or register it into the instruction register. So at this point, we fetch the instruction. OK, that's done a fair amount so far. The next thing we need to do is go get the actual operands. So in the third cycle here, we're going to take the RD, we'll say, or actually we'll take the two sources, RS1 and RS2, and we're going to fetch first RS1 from a register file and latch that or register that into the A operand. Then we're going to do the same thing for RS2 on the fourth cycle. And now we can actually do, let's say, an add. So let's say we're assuming that we're doing an add instruction here. So now we can do the add. So we let A and B actually add. And we need to store the results somewhere. Well, conveniently, we know we want to store it into the destination register. So we don't have to store it into A or B. We can actually store it back into the register file here. So we will be asserting RD as the address, and we will be the microcode control unit will be asserting register write on the register file. OK, so we've now actually done our actual operation almost completely. We next need to figure out how to increment the program counter, because we want to go fetch the next instruction. So as we said, we didn't store the program counter anywhere here. So we need to go refetch the program counter out of the register file. And we're going to reuse or time multiplex the ALU here. So we're going to fetch that value, put it into A. And we're going to increment it by 4. So the next cycle we'll do, let's say, an operation here. Let's say the ALU has a special operation just for adding 4. Alternatively, we could try to load 4 into the B register here. And we're going to add 4 because our instruction is 4 bytes long. And we're going to store that value back into the program counter. So at this point, we've actually executed a complete one instruction. And it takes, I think we added up something like 5, 6, no, I think 6 or 7 cycles at that point. Now, one of the things I wanted to point out before we move off the slide is that depending on the instruction you're executing, you can have variable amounts of time taken. So for instance, if you're trying to do a branch instruction, branch instructions are a little bit different. We're not going to actually just add 4 to the program counter. We might need to fetch a different value and do a compare, and then fetch either the program counter or add a different value to the program counter when we go to do a branch operation. Likewise for jumps. And it can have different numbers of cycles. Another good example of different numbers of cycles is if we're going to be operating on a unary instruction, or instruction which only has one input. So a good example of this is let's think, what is a good example of this? This is something like a logical negation where you just flip all the bits in a value. I don't think MIPS actually has that instruction. Anyway, what I'm trying to get across here is you can actually have different numbers of cycles to execute instructions depending on the instruction. So example, something like a load instruction would also take a lot more cycles because you're going to have to cycle the memory unit here more times. So you'll have to execute an instruction where you actually go and fetch the data from the memory and then put it back in the register and maybe do some math with it and then store it back into the general purpose register file.